So we can also derive the formula for the mean curvature in terms of these mystery tangent fields. Notice he doesn't actually explain how you calculate the v and the w such that v cross w is z. He just claims it's possible, and perhaps it is for some examples and some students. But anyway, then he gives an example, a sole example. And his example is pretty cool, so I think that's most of the reason I'm going over this section. So it's an ellipsoid, right? X over a squared plus y squared over b squared plus z squared over c squared. And that ellipsoid has unit normal field this, all right, because, well, this is not the unit normal, this is just the this is just a normal field. He divides by 2 to get rid of pesky factors of 2, which is great. And then covariant derivative of a vector field v of z. Well, you got v on this, v on that, v on that. Going back to our not curve-based, but differential operator-based definition of covariant derivative that I tried to sell you guys on occasion. And so we've got this, and then that ends up giving you. So that when you have v acting on that, only the x component cares, and you just end up with the x component of v divided by a squared, and then the y component of v divided by b squared, the z component of v divided by c squared, which gives us this formula over here. And same happens when we replace v with w. And so if you've got a dot product of a cross product, why not use the triple product formula? Woohoo! And so there it is. Z is x over a squared, y squared, y over b squared, z over c squared. Those are the components of z. The components of this guy and the components of that guy are respectively this and that. But the cool thing here is, of course, we can factor out using multilinearity of the determinant, the a squared, the b squared, the c squared, like so, properties of determinant. And then this is the xyz vector cross v with cross w. It's the triple product of xyz with v cross w. And that's kind of cool because that means that this is just, how can I say this? Well, it's this. So that we can actually calculate is, trying to think of where there's another v cross w that appears somewhere, so you don't actually have to count. Somehow he manages to get away with this whole calculation without ever actually explicitly stating v or w, which is what is just kind of like, I mean, it's cool, but at the same time maddening. Because if you're like me, you're curious, but like, how would you find v and what is w? Yeah. So k, I've lost track of something here. I think I need to go back to, come on. All right. So this was our formula. This cross this dot z divided by length of z squared. So we just worked out that this cross that for our mystery v and w works out to a squared, b squared, c squared times x dot v cross w, right? So, of course, that would be right. And oh, v cross w is z, right? Yes, v cross w is z by assumption. So v cross w is z, which is this thing. So z dot with xyz gives us this x squared over a squared plus y squared over b squared plus c squared over c squared term. And then the 1 over z to the fourth is still down there. And of course you got your a squared, b squared, c squared from that. All right, fine. I just lost track of my bells and whistles. Of course this, that's funny. Of course this is 1 because it's an ellipsoid. And so that's 1. And you've got k is 1 over a squared b squared c squared, length of z to the fourth, where z is this. So the length of z squared is x squared plus y squared plus z squared divided by, respectively, a to the fourth, b to the fourth, c to the fourth, all that squared. And there you go. That's the formula for the Gaussian curvature of an ellipsoid, which is pretty impressive. I mean, I could parameterize the ellipsoid if I wanted to, and if we did that, I mean, you could try, and I think you could probably make it through the alphabet soup of section 5.4. And maybe that's a good problem for me to assign you guys. Maybe I'll regret it. But certainly we could parameterize the ellipsoid and try to reproduce this result. Excuse me. From the parametric viewpoint, and that might be interesting. I don't know. Let me see if I can find that problem in O'Neill now that I'm thinking about it. I'll see if it's in there. But if it's not, maybe the reason it's not is because this is just way, way easier. Again, I find it really cool that you can do this calculation without ever actually finding V or W. And of course, also this gets us the Gaussian curvature of the sphere, straight. If we put A, B, C all equal to R, then this formula simplifies down to just 1 over R squared is the Gaussian curvature, right? And so this is, by the way, analytical proof that the Gaussian curvature of a sphere is 1 over R squared, whereas the argument I gave you at the start of chapter 5 was a little more sketchy. This is not. This is, you know, a gory detail. And now this, I have lost track of where I found this formula. I believe its source is Wikipedia. But here's a stone-cold formula for the Gaussian curvature based on just the partial derivatives, second and first order derivatives of the level function. Apparently, if you take this 4x4 determinant and divide by the length of it to the fourth power, this gives you the formula for the Gaussian curvature. Now, I do not know how to derive this formula, and I'd be interested to see how that's actually done. But then again, I haven't really tried hard to do it yet either, but that doesn't mean it's not hard. Right. So that brings us all the way over to my old lecture 17, which we'll start next time. This is on, of course, special curves and surfaces of revolution. So, thanks, guys.